In this particular graph, we can see that as our position increases in the positive direction, our time is passing. Okay, so as time passes, our position is increasing in the positive direction. Okay, so that means, would our person have positive velocity or negative velocity? Positive velocity, right? Because our final position is greater than our initial position. Okay? And if I wanted to calculate the velocity from a position versus time graph, I calculate the slope. Okay, so to find velocity, I want to find the slope. Okay, these are things that you're going to have to know. You're going to have to be able to interpret both of these types of graphs. So if I ask you to find the velocity of my object and I just give you a graph, that means you're going to calculate the slope of that line. Okay, at any 2 points. If my graph looks something like this, what would be happening here? Tell me what would my object be doing? Moving forward or moving backward? Moving backward, right? Because I'm starting at a position of 80 centimeters and I'm moving toward my origin again. I'm moving toward my position of 0. So I'm moving backward in this case. So my velocity would be positive or negative? Negative, right? Isn't the slope of my line negative? Yeah, so my velocity would be negative. I'm moving backwards. The negative here indicates to us a direction. Okay? What if my line looked something like this? What would be happening here? As I move here, what am I doing? Moving forward. Now what am I doing? Staying still, right? I'm not moving. My position is unchanging. Okay, my position is not changing here. So that means I walked forward. Now I'm standing still because time is still passing. It's going from 0.2 seconds to, 0.3 seconds. Finally, what am I doing here? I'm moving backwards again. So I moved forward, I stood still for a second, then I walked backward to my original position. Okay, so can we interpret that graph? It's important for you to understand, I need to look at that y-axis to determine, is it a position versus time graph, or is it a velocity versus time graph? Because that's going to make a big difference on what we calculate there. Okay? All right, a velocity versus time graph of this exact same scenario. Okay, so this is an exact same scenario. Here I'm moving at constant velocity because I have a constant slope. Right? I don't have anything changing, so I'm moving at constant velocity. At this same, we're looking kind of at the same essential picture here. This is a velocity versus time graph. So we need to make sure that we're understanding this is velocity over a certain amount of time. Okay? So if my velocity versus time graph gives me a straight line, what does that mean that's happening in my motion? Am I standing still? No. I'm moving at a constant velocity of 200 centimeters per second. Okay, so on a position versus time graph, a flat line means that I'm standing still, but a velocity versus time graph means that I'm moving at constant speed or constant velocity. Okay, I'm moving at a constant rate. All right, so there's a big difference between those two things. And we're going to talk about how to interpret this velocity versus time graph a lot more here in a little bit. But we need to understand the difference between these two types of graphs and how to interpret them. Okay, so what if I'm looking at non-constant velocity now? What if I am moving, speeding up, slowing down, whatever? Okay, so this graph, is it a velocity versus time graph or a position versus time graph? Velocity. Okay, it's a velocity versus time graph. And you just have to figure that out by reading your axes. You can't tell just by looking at what's happening here. Okay, so I just want to walk through basically what's happening in the motion. So if you want to kind of rough sketch this graph down, you can. You don't necessarily have to, but you could if you wanted to. And we're going to talk about what's happening from point A to B, B to C, C to D, all that kind of stuff. So if it helps you to sketch this out and then talk through it as we go, that's great. Okay, so I'll give you just about a minute or so to do that if you would like to. Okay, so if you have a rough sketch down, that's great. You don't need the numbers or the intervals and anything. I really just want to look at the curves of this line, okay, and what's happening. So from point A to point B, my velocity, is it increasing or decreasing? My velocity is increasing. Okay, so if my velocity is increasing, if I'm getting faster, what does that tell you that I'm doing? Am I moving? Am I staying in the same spot? Am I going forward? Am I going backward? What do you think? Yeah, I'm speeding up, and I'm speeding up in the positive direction. Okay, so I'm going faster. What happens from point B to point C? Staying at the same speed. Doesn't mean I'm standing still. It means that I've hit the cruise control. Okay, so A to B, you got your foot on the gas. B to C, cruise control. Okay, from C to D, what happens? I'm speeding up again, right? I'm increasing speed, so I've got my foot back on the gas. From D to E, constant speed. Okay, so cruise control again. Same speed. Not sitting still, going at the same speed. Okay, from E to F, what's happening? I'm doing what? Slowing down. Good, good. I'm decreasing velocity. F to G, what am I doing? Same speed. And then G to H, I am speeding back up. Okay, so this velocity versus time graph, I want you to really pay attention to what's happening here in terms of what's on the y-axis. Is it velocity or is it position? And then these slopes are going to tell you a lot about what the object's doing. Did this object probably move a pretty great distance during this time? Yeah, it never stopped moving. It moved forward the whole time, okay, except for this one little portion here where it moved, where it slowed down. Still moving forward, but slowing down, okay? We would have had to have our graph come all the way back down to 0 velocity for us to have had a stop in motion, okay? And we could have had our graph go below. What would it tell us if our graph goes below the origin or below the x-axis? Yeah, we're moving backwards, right? And in this case, our velocity would have been going from 0 to -5 to -10 to -15 to -20. So here, would they have been speeding up or slowing down in the negative direction? Would have been speeding up in the negative direction. So here we slow down, and then we turn around and we start accelerating again or speeding up in that negative direction. Okay, so reading these graphs is a little bit counterintuitive as we start going in the negative direction, but you've got to think about this 0 point as a turning point because negative now indicates to us a direction, not a numerical value. All right, very good. So we looked at the graph and what it looks like to have a change in velocity in a graphical sense, but now we're going to put an equation to it. Okay, so an acceleration is a change in velocity. So this little bar above here just means average. You can leave that off. Okay, you don't need to include that on your equation sheet or anything. Your book puts that little bar over there, so I wanted it to be consistent. I won't write that average bar over there. We're going to use average velocity all the time. So this is an equation that might want to go on your equation sheet. On your equation sheet, you don't necessarily have to write what each equation is for. Just the equation is fine. You're going to use these enough that you're going to know what they're for. But that's up to you if you'd rather write what they're for to begin with. Okay? But acceleration is change in velocity. Our acceleration is also has the ability to be positive or negative. Okay, if we're using velocity as one of our components of acceleration, does that mean acceleration is going to be a vector or a scalar? First of all, what are two things vectors have to have? And direction. Okay, and aren't we using velocity here, which is a vector? So that means acceleration must also be a vector. Okay, so acceleration has to have both magnitude and direction. That's why we say it can be positive or negative. We've got to include that direction. Okay? So when a car speeds up in the positive direction, we say it's accelerating. If it slows down in the positive direction, we say it's decelerating. Okay, so there's kind of a caveat here. These both need to be in the positive direction. Okay, in the positive direction for it to be considered decelerating. It's important for you to understand that a negative acceleration does not always mean that something is slowing down. Okay? A negative acceleration does not always mean that something is slowing down. Okay? Just kind of keep that in the back of your brain as we move forward here. Okay? And also this works with decelerating. Just because a car is slowing down doesn't mean it's going to be in the negative direction. Doesn't mean our acceleration is going to be negative. So don't try to memorize rules about positives and negative acceleration. Just do the math, and that will prove it for you. Okay? So do your change in velocity and let the math prove that what's negative and what's positive. Don't try to memorize rules about that. Okay? Okay. Our acceleration in terms of accelerating and decelerating and in terms of positives and negatives just depends on the direction of that motion and what things are doing in terms of speeding up and slowing down. Don't try to memorize the rules. Just let the math do the work. Okay. So I'm going to give you kind of a rule of thumb here for acceleration. And it might seem a little bit complex, but as we work through it, hopefully it will make a little bit more sense to you. Okay? If an object is slowing down, the acceleration is in the opposite direction of the motion. Okay, so here you could also put the sign of acceleration. So it's positive or negative. The sign of the acceleration is going to be opposite the direction of the motion or opposite the sign of the motion. So I'm going to give you a couple examples here that lets the math kind of show us how this works. Minus initial. Okay? So let's say I have an object that goes from an initial velocity. V sub 0 is what your book calls initial velocity because it's at 0 time. Okay, V sub 0 is what your book calls initial velocity. So if I'm going from initial velocity of 15 meters per second to a final velocity of 5 meters per second, am I slowing down? Yeah. Okay? And let's say that it took me 2 seconds to do this. Okay, so can we imagine what's happening here in our picture? Okay, our car is going quickly at 15 meters per second, then it's slowing down in a time frame of 2 seconds. So if I solve for acceleration, my acceleration is equal to final velocity minus initial velocity over time. So here my acceleration goes from 5 to 15. I'm sorry, 15 to 5. So here's my final minus initial over my time. What do I get for my acceleration value? -5. Okay? So here, although I was moving in the positive directions, my acceleration is negative. Okay? So I was slowing down, which means my velocities were both in the positive direction. I was slowing down, so the acceleration and the sign of my acceleration is going to be an opposite. And it makes sense, I think, for this because we're thinking slowing down, so negative. That's not the case. It only works when we're looking in the positive direction. I'm going to show you now one that's working when we go in the negative direction. Okay? Any questions about how we calculate that? Do you have a guess as to what the units for acceleration might be? Meters per second squared. Meters per second squared. Okay, so let's look at another example here for our rule of thumb. This time moving in the negative direction and slowing down. Okay, so if my initial velocity is -20 meters per second, and my final velocity is -2 meters per second, Can we see that I'm slowing down here? Even though it appears that -20 is a larger negative number, okay, that we're moving 20 meters per second, but we're moving in the negative direction. So we're moving at a quick rate, we're just moving backwards, okay? So now we're moving at 2 meters per second as our final velocity, and it's still in the negative direction, Okay. Let's say that it took us 3 seconds to do that. Okay, so that means acceleration is equal to -2 minus -20 over 3. What happens when I have two negatives? Yeah, it becomes an addition problem, so that means I get an 18 over 3, which means my acceleration is positive 6 meters per second squared. So even though both my velocities were negative, I've got a positive acceleration. Okay? So as I'm moving, as I'm slowing down, my acceleration is going to be an opposite sign of what my velocities were. This will apply, the rule of thumb will apply a lot more when we start looking at graphing again, but I want you to see that mathematically it works. Okay? So if you'd rather just let the math do the work, that's fine. If the rule of thumb helps you, great. If it doesn't, great. Okay, but I want to show it to you so you have that kind of background a little bit. Especially as we get into graphing, it's going to make it in time. Okay. Delta V over delta T. So for these word problems, we have to start really using context clues and using words that tell us what the initial velocity is going to be and what the final velocity is going to be. Okay? So if it tells us that it's increasing from 5.0 meters per second to 7.5 meters per second, what would our initial velocity be? Good. So again, your book uses v sub 0 as initial velocity because it's at 0 time. So our initial velocity is 5. Our final velocity is 7.5. So are we speeding up or slowing down? We're speeding up. Good. So our final velocity is 7.5 minus our initial velocity over time. Okay, this is where our units comes from for acceleration. It's meters per second divided by seconds. So that's where meters per second squared comes from. Okay. Oh, I'm sorry, I put 1.5. It's 1.25. All right, so that gives us our acceleration equal to 2 meters per second squared. 2 meters per second squared. Okay, go ahead and try this one on your own. Okay, so using our clues from our word problem, what variable should we have been solving for here? How long it takes. Okay, so if we have acceleration equals change in velocity over change in time, we were given our acceleration. We need to be able to start picking out variables based on units alone. So we know acceleration is meters per second squared. So this is where I talked about we're going to read our word problem, all that kind of stuff. So I know my acceleration is equal to 2.6. Here I'm making my list in the margins about what's happening here. 24.6. Velocity final is 26.8. Then here's my equation, and I'm going to plug it in. 2.6 equals 26.8. Final velocity minus initial velocity over time. Okay? Do the subtraction here, which comes out to be 2.2. Over t equals 2.6. So yeah, when your variable is on the bottom here, you're going to switch those two places. Okay, which means t is equal to 2.2 divided by 2.6, which gives you a time of about 0.8 what? 0.85 in units? Seconds. Good. Do we all agree? Yeah. Did that come out in your calculator okay? Yeah. Okay. Good. Very good. Any questions there? Okay, good. That's basic velocity and basic acceleration. We need to understand that these two are not the same thing. They tell us two very, very different things. Okay? Velocity tells us the rate at which our position is changing. Okay, the rate at which our position is changing. how many meters we're covering in a certain time frame, or how many centimeters, or how many whatever kilometers. Okay, it's telling us the rate at which our displacement is changing. But acceleration is telling us the rate at which our velocity is changing. So how quickly are we speeding up or slowing down? And so it tells us two very different things. Let's go ahead and try this one on your own as well. Car accelerates along a straight road from rest to 75 kilometers per hour in 5 seconds. What's the magnitude of the average acceleration? So there's a couple things that should jump out at you here. What do we see in this term and this term? Our time units don't match. So there's a couple different ways you could do this. You could convert your velocity to meters per second, or you could convert your time to hours. You can choose whatever one you would rather do. Okay? Go ahead and solve that on your own, and we'll see if we match. What does this from rest tell us? Yeah, that what is 0? Initial velocity. Good. Our initial velocity is 0. Is that about what you had? Or not so much?
54,000? Okay.
Because this is meters per second per second. If you did it in kilometers per hour, you get about 54,000 kilometers per hour squared. Okay, so the reason we don't get the same numbers is because we're not in the same units. We see something extremely different. Okay, so I converted my 75 kilometers per hour to meters per second, and I got a velocity about 20.8 or something like that. 20 point something. And then I take final minus initial over time. Okay, so there's a couple different ways you can do that. So let's talk about a conversion factor that helps us convert from kilometers per hour to meters per second. Okay, most of the time we're going to want our velocity in meters per second. Okay. It happens sometimes that kilometers per hour will work, but for the most part, we need it in meters per second because gravity is given in meters per second squared, right? Which means we're going to do a lot of things dealing with gravity, so we need consistent units. Okay, so let's try a conversion here from 75 kilometers per hour to meters per second. If you just did it in the last problem, you already know what your answer should be, right? Okay, so if I want to go from kilometers per hour to meters per second, I need to go from kilometers to meters. So 1 kilometer equals 1,000 meters. 1 hour equals 3,600 seconds. Okay, so every time that you would convert from kilometers per hour to meters per second, wouldn't this part of your T-chart look the same? That would look the same every single time, right? So tell me what the value is for 1,000 divided by 3,600. Yeah, 0.2777778. Okay, so what I want you to do is this. We're going to kind of create a little shortcut here. If I want to go from kilometers per hour to meters per second, I'm going to multiply by 0.2778. You don't have to use a shortcut now. But it's going to speed things up. So if I want to go from kilometers per hour to meters per second, I would multiply. If I need to go the other direction, what would I do? Yeah, divide by 0.2778. Okay, you can do the t-chart. The t-chart will work every single time. This is just a little bit of a shortcut to help speed that process up. Okay, and if you don't want to use a shortcut again, that's great. You can write this shortcut on your equation sheet if you want. Okay, but it's just something that would help, may be helpful for you. The t-chart will always work, but this might speed it up. Okay? So, when you do it the long way, let's see here, 75 times 1,000 divided by 3,600 gets us 20.83 repeating. If you take 75 times 0.2778, do it and see if it works. 20.835. That's pretty close. Okay, so it gives us that same value. Alright? So use the shortcut, don't use the shortcut. I really don't care. I give it to you in case you want it. Okay? These things with a partner, I'm going to give you 2 questions here that I want you to, like ponder a little bit. Okay? And we're going to talk about them. So I'll give you about 4 minutes or so, 5 minutes to think about these, and then we're going to discuss what our answers would be.